Okay, let's humble ourselves for a prayer. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Oh Lord, we thank you for this night. We thank you for everything that you have been leading us into yesterday. Lord, we thank you for everything that you have passed through this night. We thank you for the good breath. Many have died, but who are we to wake up? Lord, we are showing you this day. Lord, we request you to guide us through this day. We request you that whatever we are going to study, we can understand it. In Jesus' name we have prayed. Amen. In the name of the Father, and the Son, and of the Holy Spirit. Amen.
Thank you so much for the word of prayer, Matthew. Good morning once again. Thank you so
Yes.
much. Okay. Thank you so much for keeping time. We are good to start. So, in our session today, we are going to look at graphical interpretation and curve sketching. So, that one should be your heading. Graphical interpretation, depending on the book you'll be reading. Yes, in some books you may find them just calling it curve sketching. More so if you look at the at the old books, yes, mainly in the old curriculum, they used to call them curve sketching too. Curve sketching too. Okay, okay. And I'm going to take an assumption that we have finished to put our heading down and we are going to start now. What are we going to do in this particular section? One, we are going to develop those graphical skills to enhance our reasoning and visualization in solving real life contexts, such as in optimization. So we are going to mainly be looking at how can we sketch. So that is where we are going to look at how can we sketch graphs. So that is what we are going to look at. So we are going to look at different graphs and then we learn how to sketch them using knowledge from different aspects, from different angles. That's what we are mainly going to look at in this particular section. And what are some of the key things that I want you to look out for? So I want you to take note of these words. Words like intercepts, words like asymptotes, words like range, words like domain, words like increasing, decreasing, concavity, turning points. Yes, those are some of the words. So take note that even when you are making your personal research, these are the words you look out for to know the meaning. But also, when it comes to curve sketching, these are some of the words we are going to be looking at. Okay, let me assume members have finished to take note of those words. Okay, are we good to go? You can let me know through the chat whether we are good to go. Okay, Matthew says yes. All right. Okay, from there. Now, under this section, we are going to look at what we call uh, rational functions, but at a later time, we shall bring in an idea of what we call irrational. Now, what are we going to look at? Now, when they talk about rational, when you look at this word here, it comes from the word ratio. You see the word ratio. And when we talk about ratio, many of you know that it's like writing A to B or writing A out of B. Now, when I talk about a function, a rational function, it means that that is that kind of function we can write in form of a ratio. Whenever you have a function that you can write in terms of a ratio, like you have two ratios that you can write, then that one qualifies to be called a rational function. In other words, a rational function is that one that can be written in the ratio of two polynomials. If I can write something in a ratio of two polynomials, then it means that that one is a rational function. Hope that is okay. So whenever I talk about a rational function, one of the properties is that you must be able to write it in terms of a ratio. Now, on top of writing it in a form of a ratio, that one must be a polynomial. Must be what? A polynomial. So you must be able to write it in terms of two polynomials. So that is what I'm saying, and that's what we are going to look at in our session today. Now, after doing so, I can give you an example. Take an example. When I'm talking about a rational function, is that when I have y equals to x plus 1 out of x minus 1. Now, this one is what we call a rational function. Remember, y is the same as your f of x. Now, my f of x here is x plus 1. My g here, for this case, is x plus 1. My g of x is the same as x minus 1. So that means that this y of ours, we can write it in terms of x plus 1 and x minus 1. And therefore, this is called a rational function. Even if I have this, as long as you can write it in terms of polynomials, even if I have x minus squared 1 out of 1, then x plus 2, and then I have x minus 3. Also, this one qualifies to be called a rational function. Why? Because you can write it in terms of two polynomials. When you look up, this is a polynomial. When you look down, you note that also that one is a polynomial. So that is what we call a rational function. That one, we call it a rational function. Hope that is very okay. I can give you another example. I want you in the chat to tell me whether this is a rational function or it's not. I have this x squared plus x minus 2 out of x minus 1. In the chat, tell me, is it a rational function or it's not? So your answer should be yes or no. And always take note that when it comes to a rational function, you cannot simplify it further beyond that point. So what do I want you to do? Always first check. Is there something, can the numerator and the denominator cancel? Is there something that can cancel? If you find out that they can cancel, then it means that one is, they can cancel and it dies away. It means that it's not a rational function. So always I want you, when you face that quadratic equation, when you notice that it is a quadratic expression, always first test. Ask yourself, is it rational? It's not. So can you first test before you say yes or no? That's what I wanted you to first check out. Look at what they have given you. If you find that the numerator and the denominator can be reduced further, then it means that one is not a rational function. So can you check and tell me through the chat? And check out. If you find out that what you have up and down can be cancelled, then that one qualifies not to be. I don't know, maybe it's not. It's not. Very good. Members, you can notice that when you look at the upper one, it is the same as having x minus 1. And then here you have x plus 2, everything divided by x minus 1. You notice that these ones can cancel, and therefore you get y is equal to x plus 2. Now, y is equal to x plus 2. Members, this one is not a rational function. So here you cannot say that this is a rational function, because remember, a rational function, you must be able to write it in a ratio of two polynomials. Yes, whereby those two polynomials, you cannot reduce any further beyond that point. So this one is not a rational function. Okay. Hope that is very okay, members. Always check what you have. In case it can be reduced, then go on and reduce. Members, what about this? I have this. I have this. I have this. I have this. Let me know. Let me know. What about that one? My y is equal to x plus 2x squared plus x minus 2. Is it a rational function or it's not? So check out again. You check out. Don't just make a conclusion and say, hey, it is. Just mere looking at it. Always check out. Most so now when it comes to those quadratic ones, if they are linear functions, that one it is okay. You can easily use your eyes to see. But if they are not linear functions, then better you test out and see. Is there anything I can factorize out to get this? If it is, then you say, yeah, 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 yeah. If it's not there, then you say, no, 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 no. Okay, looking through the chart. Uh-huh. It is not. Uh-huh. Now, this is where now I want you always. You have to go on. Many of you are saying no. Okay, let us go on and say this is x plus 2, whereby this is x squared, but it is. Dr. Jime says yes. Dr. Jime, if you could unmute and tell us why you say yes. Shadow is also saying yes. I don't know. Shadow, if also you can tell us why. Oh, Shadow, go on. Okay. Gilbert?
Yes, sir.
Hmm.
Uh, it is a rational function because, like, when you simplify the denominator, you get
Hmm.
x plus 2, then x minus 1. And the
Hmm.
x plus 2 can reduce with that one up, then you remain with 1 out of x minus 1. And that one is still a ratio.
Okay. Perfect. Perfect. Thank you, Gilbert. Yes, now members, here I want you to take note. Yeah, even if these ones cancel and you remain with this one, this ratio is far different from x plus 2. So this one, members, qualifies to be called a, a rational function. Because when you look at this one I can write it in terms of a polynomial. In terms of what? A polynomial. This one means that the polynomial is there, but just because it is of degree 1, like it is just 1. So this one is a ratio. This one is not a ratio. Members, I don't know that you have got the difference, that this one, we shall treat it as a rational function, whereas this one, we shall not treat it as a rational function. When you look at this one here is okay, and x minus 1 is okay. So there is a very big difference between this and remain with x plus 2. Members, have you got the difference between the two? Kindly let me know through the chat. So whenever you have that inverse proportion, it means that that one qualifies to be a rational function. Whenever you have that inverse relation, it means, but if it is just direct proportion, like this one cannot be called a rational function. Okay, now that is what is very important. Now we are good to go. So having understood rational functions, then what about we have other functions we call irrational functions. So when I talk about irrational functions are those particular ones whereby you cannot express them in terms of a ratio, but in most cases these are the functions we are going to write in terms of roots. Whenever you find a root, take an example, if I have, let me say, y is equal to root of x. These ones we shall call them irrational. Irrational functions. So we shall, at one point, we shall look at these ones, whereby you have y is equal to root of x plus 1. Now, these are what we call irrational function. There is no any way you can write it in terms of a ratio of something. So whenever you find such, then that means that you are talking about what you call irrational functions. Okay, yeah. Things like whereby you have found they have told you sketch this x minus 2. These are called irrational functions. Even they can set it for you in this format. Y is equal to x. You squared. Y squared is equal to x. Members, have we got the difference? Have you got the difference between rational and irrational? And are we good to go? Okay, okay, very good. Okay, now from there, allow me to take you and I show you how do these rational functions look like on a graph. In case we're on the graph, how do these functions look like? What is their nature on the graph? So take an example. I can have my first one, y equals to 1. Okay, I'm going to show you the difference between the other function we had, like where we remained with x plus 2. Are you noticing? When we have y is equal to x plus 2, this is the kind of thing we get. Whereas if I have, oh, okay, wait, x plus 2, let me show you the difference. Whereas when I have y equals to 1 out of x plus 2, members, are you noticing the difference? Someone can tell us the difference. What difference have you noticed? When we have y is equal to x plus 2, and I have y is equal to 1 out of x plus 2. So who can give us the difference? Those functions that are rational. What are you noticing about them? The kind of graphs we get. Yes, Andrew. And then we shall have Gilbert. Yes, Andrew, unmute.
For morning, teacher.
Yes, good morning.
For rational ones, the one is forms a straight line, and another one, and this second one forms a curve.
Okay, thank you. Yes. Now, the first one is what we call a linear function. The first one, we call it a linear function. The second one, we call it a rational function. Gilbert. Okay.
Well, when I look at the graph, like the first function, which is not a rational function, like when you put it there, it formed just one line. That's a line. I don't know whether if the function is of a curve, it forms a curve, but it is just one. And when you put the function of the rational function, it forms two curves.
Okay, good. As we go on, allow me, Ruth, as you come in, thank you. Allow me to add another function. Allow me to add another function. Allow me to add another function. So Ruth, for you, your difference is going to come from the 3. I've added another third function. Let me even change its color. And you tell us what you are observing also. Ruth, go on.
Okay, so the first function is just a straight line. Sorry, it forms a straight line. Then the second one, with exception from what the previous presenters have said, I see a vertical asymptote at -2, And then I see a horizontal asymptote at what? At 0. Then the vertical asymptote is at -2, 0. Then the horizontal one is at 0, 0. Then for the third one, the third one is just it sets from -2 and moves to the right as a curve, a mere curve. I don't see any asymptote that it holds. So yeah.
Okay, okay. Thank you. Okay. What about the number of curves it forms? What have you noticed
Oh
about it?
yes. Okay. Yeah, it forms one curve.
It forms one curve, yes.
One
So
curve.
members, okay, thank you. Yeah. So members, you can notice that when we had this red one, you notice very well that for it went on, it gave us two curves. When it came to the green one, here, you got one curve. Then for the first one, you got only one line. So there is a difference. The first one, we call them linear functions, that one, that line. So linear functions, they'll give you a line. Then when it comes to these ones, rational functions, they will give you those curves, two curves, or more than that. Then when it comes to these irrational ones, they give you one curve, but also their shape matters. Their shape also matters. What about if at all I had put it like one out of this? Oh, let me see. X plus 2. How does it look like? I want to remove this. I don't know that also you have noticed that for it, as long as it is irrational, you'll always have just one curve. So now that is the difference between rational, irrational, and then the linear functions. So what are we going to look at today? I want us to first look at the different things we are going to be looking at. Allow me to change this, and I want members to observe very well. I want members to check out these curves we have come up with. I want you to let me increase such that you can be able to see them clearly. Members, I want you to look at these curves we have formed. You tell me, when you look at these curves, we have two lines. We have what we call an horizontal line. Let me say these are our horizontal lines. And when a line passes through this point here, we shall say that this point here, this line here is what we call y equals to 1. When a line passes through here, we say that that is the line y is equal to 2. However, if our lines run vertically, take an example, if our line comes like this and it passes through this point here, members, what would be the equation for that line? Oh, wait. It is passing through this point here. Let me draw it again and tell me what would be the equation for that line. If our line comes like this, what would be the equation of that line? I want to see whether people remember. X is equal to -1. X is equal to -1 because our line here is passing through -1. So all the X values are constant, but Y values are changing. Very good. Now we come back to another concept. I want you to observe these curves and tell me which vertical line do both curves don't touch? Which vertical line? And put your answer in the chat. Which vertical line is that whereby you notice that these two curves are not touching it at all? Both those two curves are not touching it. People are saying x is equal to 1. X is equal to 1. I want members to look here. Very good. Thank you for that observation. Members, when you check here, you notice that our curves are coming towards this vertical line, but they are not touching it. Even this second curve, you notice it that it comes towards 1, but does not touch it. Very good. What about, you tell me, which y line, which horizontal line are these curves not touching? They are reaching there, but they are not touching. You are not seeing it being touched. Even if I try to move this graph of mine, you will notice that however much we go, are you noticing? I'm trying to extend to show you that even if I extend up to somewhere, they just approach it, they don't touch it. Even this second graph, when you look at it, whether I have gone up, whether I have gone down, you notice that it is not being touched. So which line is that you are noticing? The horizontal line. Ah, the horizontal line, Matthew, Akram, very good. Members, you'll agree, you'll notice that when you look at the horizontal line, you notice that when it comes to this line here, it comes to this line here, our curves are not touching it. And members, these two lines where our curves do not touch, they appear as if they are approaching them, but they don't touch, are what we call the asymptotes. That is the mathematical word. We call them asymptotes. They appear as if they are going to touch, but they do not touch. They are approaching these lines, but they do not touch. And those lines, we call them asymptotes. Now, when your line is vertical, this is what we shall be calling the vertical asymptote. When your line is horizontal, we call it the horizontal asymptote. So when I tell you I want a vertical asymptote, when you look at the answer you wrote for vertical asymptote, you say that vertical asymptote, your x was equal to 1. When you were mentioning the horizontal asymptote, you say that your horizontal asymptote, your y is equal to 0. Now, you need to know, when I talk about horizontal, you are going to mainly read the y. When we talk about the vertical, you read of the x. Allow me to put another curve. Allow me to put another curve. Any question on that before we go? Because now you're going to first identify for me the asymptotes. I'm going to draw different graphs, and then I want you to be identifying those different asymptotes. Are we together on that, members? Is everyone fine? I want now to draw. And then you tell me that what you have drawn, its vertical asymptote is this, its horizontal asymptote is this. That's what you are going to be putting in the chart. You put V for vertical. You put for me H for horizontal. Okay, I start with the first curve. With the first curve. You tell me, you tell me, you tell me what you are seeing. You look at that line where the curve reaches vertically, it's not touching. Horizontally, it's not touching, but as if it is reaching there. So you put V, what is your vertical asymptote? What is the horizontal asymptote? Put V equals to that vertical. Put H to represent my horizontal. Sammy says V, both curves, you look at both curves. You look at both curves. Don't forget, you read the y coordinate. You write it in equation format. Write it in equation format. You say v x is equal to -3. Thank you. You say y h is equal to 0. A member is not saying that. Anyone we are leave? Okay. Thank you, Shadow. Thank you, Maria, John, Abe, Moses. Very good. Very good. Dorcas. Yes. The answers coming. Matia, Linda. So, Linda, we are saying that we are looking at that particular line where our curves do not touch as they approach. So when you look at our curves, you notice that when these curves are coming and they reach this line here, you notice that they are not touching it. They just go, but they don't touch it. When you look at this line horizontally, you notice the same behavior. Our curves approach, but they do not touch. So those are what we call the asymptotes. Mathematically, we call them asymptotes. Okay. I hope, Linda, we are there. So I'm going to delete this and I draw another line. I draw another line. I'm going to draw another line. And then you told me. I have another curve. I have other curves here. Let me see whether I can reduce. But when I reduce it, okay, the scale becomes a bit big. Okay, I have reduced. But let me increase because there is a value you may not see. Yeah, somewhere there. You're right. What is your vertical? What is the horizontal asymptote? Look out on the curve. Gilbert says x is equal to 2, y is equal to 1. Okay, x2. Cedric, vertical is 2, shadow x is 2. Maria, h is 1. Matthew, Omra, John, very good, very good, very good. Okay, 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 perfect, perfect, perfect. Okay, okay. That's good. Now, those are what we call the asymptotes. Those are what we call the asymptotes. Now, another thing, I want you to tell me, I want you to look at one of the curves that we are coming up with. You tell me, when you look at those curves, I'm going to make it bigger. But I wanted to just bring to your attention that this is how these curves appear. But I want you to check out and tell me at what point, what coordinate on the x-axis and on the y-axis do these what's up? Okay. At what point At what point on the x-axis and on the y-axis do the read for me the coordinates of the x-axis and the y-axis where this curve is touching? What could be that coordinate? What coordinate are you able to read? On the y-axis, you tell me on the y-axis and you tell me on the x-axis. What coordinate is this line or is this curve of ours touching? What coordinate is that where our curves are touching? Which ones are you able to observe? Someone is saying -1 and -0.5. Very good. So when you notice here, you notice that there is a point here, there is a point here, and there is a point here. Now this point here is what we call the intercept. This point here is what we call the intercept. Now you need to know that you may have those, like you have noticed, we have the two curves, but one has an intercept, another one does not have an intercept. So when you look at this intercept, this axis here is what we call the x-axis. Now for such, those ones we call them the x-intercept. This is the y-axis, so these ones we call them the y-intercepts. Now going forward, you are going to read for me two things. You are going to read for me the intercept in case the curves have, and then you read for me the asymptote. When you are giving me the asymptote, I want you to give me the vertical and horizontal. But this time around, tell me the vertical is x is equal to this. Horizontal, y is equal to this. Only. But look at the curves we are coming up with. Y is equal to so 1. Oh, wait. Let me make it better. Okay. Look at those curves. Hey, I want you to read for me the intercept, and then you read for me what our asymptotes are. I don't know whether it is clear or I need to reduce a bit. Let me reduce up that point. Hey, I'll put some of these points such that look at those lines. For whatever line you see that the curve is not touching, you read it. So, read. So, someone is saying our y. Read the coordinates that you are seeing. I don't know where people get y is 0.5. I think Andrew is talking about the intercept. That is going to be my assumption that you are talking about this intercept. X-intercept, x is equal to 1. Vertical asymptote, we have -2. And please take note that you may have more than one asymptote. Don't just look at one. And there are cases where you don't have any. Now, for such a case, okay, thank you. Thank you. Now, for such a case, you are noticing that when you look at the curve, this is one of the lines they don't touch. When you look at the curve, this is another line they do not touch. So, what I want to bring to your attention is you can have more than two asymptotes. And you may have a situation whereby you don't have an horizontal asymptote. Hope that is okay. You may have a situation where you don't have an horizontal asymptote, but when you have what you call let me say, an oblique asymptote. So when you look at such a case, what are you noticing? You are noticing that you have this line here, you have this line. So you have two vertical lines. And now these are our vertical asymptotes. So you are noticing that if the curves are here, it crosses this one. So remember, an asymptote, the curve doesn't touch it. So the curve does not touch it. Now for such a case, you only notice that you have only vertical asymptotes and there is no horizontal asymptote. Take note of that. Here we don't have an horizontal asymptote, but we have a vertical asymptote. Number two, these are our intercept. We have this intercept and then that intercept. So those are the two things we do have. May I know whether members through the chat you have picked the idea of what an asymptote is, what an intercept is? We don't have a weak asymptote. We don't have a weak asymptote. We have mainly three. It can be either a vertical, it can be horizontal, or it can be a slanting, or what we call an oblique asymptote. Very good. Now, the last part is the point where, are you seeing these curves? When you look at these curves, they have a point where they curve from, like here, like here. Members, how did you call that in differentiation? That point where the curves are, Moses, an intercept is this point where your lines, your curves meet the x and the y axis. You called them turning points. Very good. Turning points. Now that is the other thing we are going to look at. The turning, yes, favor. That's okay. Linda, turning points. Now for the different curves we are going to be having, we are also going to come up with what we call the turning points. So you are going to come up with those turning points such that you know at what point does your curve turn from. Like here, you need to know at what point did my curve turn on such that I get such a curve. When you look at this, you ask yourself, at what point was this that the curve turned on? So those are the different things we are going to be looking at. So when we are making this, we are coming up with the sketches. These are the sketches we are going to be coming up with, members. You'll find your sketches like that depending on the graph and depending on the rational function. Okay, in case you have a hand, any question we may ask at this point. Yes, Gilbert.
Yes, sir, for me, I have one question. Like you talked of an oblique asymptote.
Mm,
Can you illustrate for us one? Just want to see
okay,
how
and
it looks.
you want to see how it looks? Okay, no
Yeah.
problem, no problem. Let me get for you one. Now, when it comes to that oblique, let me give you one. But let me delete this. Uh, Let me delete this and I give you y equals to x squared plus, x squared plus 1 out of x plus 1. Why did I use 1? Let me see whether when I use 1, it comes out the y1. X squared plus 1. Okay, let me add something. Okay, let me make it a bit better. 3x. Then here I put maybe plus 1. Something like that. Are you seeing this thing?
Yes, sir.
Now, an oblique, in case we are looking for the what? To get the oblique. When you look at those curves, Are you not seeing? How would you think the line where those two curves are not touching is going to pass? How do you think it's going to look like? Members, put in the chat. We have those two curves. When you look at them, where is that line where those two curves don't touch? Where do you think it's going to be? Like, how is its shape going to look like? Jimmy says slanting, linear, very good. So you notice that for such a line, like shadow between, very good. That's perfect. Yes, it's going to be between. So you'll find that the line is somewhere here, where those two things are not going to touch. I don't know whether it is now clear. Is it clear now?
Yes.
So
Yes,
that's
but
in the middle. So now when it comes, we are going to look at what is that line. What is that line? Now that line looks like that. Here I've just put for you but I will show you how we get there. But when you look at it, that is the line that you'll have to get. That even if I extend the curve, you'll see that this line goes very close, but the curve doesn't touch it at all. Hope you are noticing that even when I extend up the other side, the line goes, but the curve does not touch it. Even if I go on to reduce, you will notice that the line goes, but the curve will never touch it. It just passes at that point. And now that is what we call an oblique, or what we call a slanting asymptote. And for it, I want you'll take note that always the powers in the denominator are the ones, like when the power in the denominator is more than the power in the numerator, you get such graphs. You just look at up and down, and then I can give you another one. As long as you have that kind of concept, you see it like that, you notice that. Let me say I have y, I have maybe x power 3, and then I have plus maybe 1, okay, maybe plus x, then you divide, I wanted everything divide by maybe x minus 1. Okay, this one may not be x plus 2. Okay, that is, now this one will come out like that. But mainly, cases where we get such curves, it happens when you have a curve. Oh, sorry. Now, when you look at this curve, this one doesn't bring that kind of asymptote. So meaning it is not. But why is it not bringing? Is because the power, whenever it comes to those slanting asymptote, the highest power in the numerator should be just one more than the power in the denominator. Just one more than that. I will show you this, how it comes about. As long as it is just one. So those are the cases where you will get such curves of slanting. Okay. I don't know whether we are good to go, members. Are we good to go on that? Gilbert, is that fine?
yes, it's fine, sir.
Okay. Any other question? Or members, we are good now to start on the numerical part of it. Okay. Very good. Now allow me that now we go back and then start. So I want you always, whenever you are doing such numbers, always have those three things we have talked, those three things we have talked about. We have talked about asymptotes, we have talked about intercept, and now we have talked about the turning points. So those are the things we are going to be dealing with. So the first one is I want to bring to your attention what you call the intercepts. Like you saw on our graphs, that an intercept is that point on your graph where your curve cuts either the x or the y axis. As long as you get that point where your curve cuts, then it means that is what you call an intercept. Now you have two intercepts. You can have either the x or what you call the y intercept. So those are the two intercepts we shall have. Because here we deal with mainly x and y axis. In case we had 3, then we would have had the z. So the first activity we are going to do, we have this, that activity 1. Activity 1. Find the x and y intercept. Intercept for the function. For the function. I have y equals to x plus 2 over x plus 3. This is our function. Now, here, we are going to do it together for now, then I'll give you one to try. Now here, when we are finding the x-intercept, and when you are giving this intercept, you give it in form of a coordinate, because it is a point, so you read it as a coordinate. So when it comes to x-intercept, it means that our y is going to be equal to 0. So what do? You'll come and say my y is equal to x plus 2 out of x plus 3. So what does it mean? It means that where there is y, we shall put 0 equaling to x plus 2 out of x plus 3. Now at this point, you can do your cross multiplying. You cross multiply. So you notice that you have 0 times your x plus 3 is equal to x plus 2. So here you get 0 equals to x plus 2. And therefore your x will equal to negative 2. Now that means that your x-intercept, x value is going to be negative 2 and y will be 0. So along the x-axis, you'll find that the point is negative 2, 0. In case we are finding our y-intercept, still we do the same thing, that for y-intercept, our x is equal to 0. So you come and say I have x plus 2 out of x plus 3. So where there is x, you substitute 0. So we shall have y is equal to 0 plus 2 out of 0 plus 3. So your y will equal to 2 out of 3. And therefore, at this point, our coordinate is going to be our x, which is 0, and then our y, which is 2 out of 3. So that is how you obtain the intercepts. Members, hope we are on the same page. Is that fine to everyone? I'm taking an... Okay. Okay, yes. On track. Teacher, no. Okay. Same page. Okay, Moses. Others, now I'm giving you the second one you are going to try as I pick on Moses. You find for me the intercepts for this. 3x plus 6 out of x minus 1. Find for me the intercept as I pick on Moses. Moses, kindly unmute.
Good morning, sir.
Yes, good morning.
Yeah, teacher, I'm really sorry. I was changing my device. It had shut down. That's how you left me. I'm so sorry about this.
Oh, what I'm saying
Mm.
is one, when we are finding the x-intercept, where there
Yes.
is y, you put 0.
Yes.
Then you do like how we have done. In case I'm finding the y-intercept, where there is x, put 0.
0.
And then you get the coordinates.
Okay. You just
Eh,
replace with the given
yeah,
coordinates. Okay.
yes. Mm,
I got it. Thanks so much, sir.
mm. Okay. Okay. Looking through the chat. I'm not seeing. People have got the coordinate. People have got the coordinate -20 and 0, -6. Very good. That's perfect. Okay, in case you are not getting, kindly let us know and then we support you. But like we said, to get the x-intercept, substitute in y is equal to 0 and you'll have, but here don't forget to reduce. And in case for the other one, also do the same. Then I want to give you one more. And I want also to bring to your attention that sometimes you may find yourself having more than 2 points for the intercepts. Yeah. Okay. Find the x and then the y-intercept. In case you feel we are leaving you, kindly let us know. Yeah. But from the chat, Shima, Samsung, Lydia, Abel, Rogers, Lydia, I'm seeing Deborah, Linda, Tim, Jimmy, Emma, Mattia, Lillian, Bettina, Sobra, Gilbert. Yeah, the answers are very correct. So can we also find for that number 3? Okay, looking through the chat, I would like to say that the answers are okay. the answers. Okay, I'm saying yes. Shadow and Jimmy. Okay. Okay. Yes. Oh, but I don't know. Some people are getting 5. I don't know how they are getting 5. But when you look, I don't know where you are getting 5. But anyway, so because remember for the y-axis, for the x-intercept, our y will be 0. So there we have x minus 1, x plus 2 is equal to 0. This is for the x-intercept. And therefore your x minus 1 will equal to 0, x plus 2 will equal to 0. So your x will equal to 1, your x will equal to negative 2. So meaning that your coordinate for such will be 1, 0, and then negative 2, 0. So that one is very fine. Then we said for y-intercept, where there is x, you put 0. So I'm saying here 0, this one becomes 0, this one becomes 0, this one becomes 0. So up we shall have negative 1 times 2 out of 4 times 1, which gives us negative 2 out of 4. But for this one, you can reduce. Oh, so by 2, 1, by 2, 2. So I expect your coordinate to be 0 and negative a half, or negative 0.5. That is our y-intercept. Yes, go back, that's okay. Please do not forget, oh, people I think added Abe. We do not add, we do the multiplication. Harmony, you look out where you are getting the 2 out of 5. Okay. Members, is the concept fine? Are we good to continue? Okay. Okay, yeah. The concept is there. Good. So we can continue to the next one. So those are intercepts. Then we have what we call the asymptote. Now, an asymptote is that line on our graphs where our graph approaches but will never touch or will never cross. And this occur as the curve is coming from negative infinity or positive infinity. And we have basically these three: vertical, horizontal, and oblique. May you summarize something from this slide before we continue? Summarize something from this slide in your book, and then we continue. Okay. Okay, people. Okay, I think people have finished. So we are going to look at one by one. We shall start with the vertical asymptote. Now, a vertical asymptote the way you saw on our graphs, they will always appear in a vertical format. And that is sometimes we may call it the X asymptote. So that is the one that occurs when our graph approaches this vertical line. Now, what does it mean? In order for us to be able to get that vertical asymptote, what do we need? We always have our denominator equated to 0. You get your denominator and then you equate to 0 for that rational function you do have only. So to get that vertical line, you get your denominator and equate to 0. An example, I have activity I can write here. For our activity, we have y is equal to 3x plus 6 out of x minus 1. We are finding the vertical asymptote. So to find the vertical asymptote, what do? We are going to equate our denominator to 0. So here, when you look here, the denominator, always do not forget we have numerator out of the denominator. So for this case, our denominator we have is equal to x minus 1. So we get this denominator we equate to 0. So I will say x minus 1 is equal to 0. And therefore our x will equal to 1. And that's what we call the vertical asymptote. Members, is it very okay? Hey, if you want, I can allow me to show you such that members can see it, how we are getting it. When I come back here, I'm going to change. Members will just look at it and then you'll see how it comes about, whether it is true or not true. Yes, so you can notice that this is the curve we have. So when you look at the vertical asymptote, when you look at that curve, you notice that, okay, let me, I think, reduce and you look at where 1 is. Okay, 1 is not coming. When you look at where 1 is, you note that is the point where the curve doesn't touch. So for such a case, that is what we call the vertical asymptote. So that is this line here that runs vertical, that this curve doesn't touch and the other curve doesn't touch. Okay, so that's how it comes about. Okay, I'm going to go back. Members, is that verifying to everyone? Okay, so that is what we call the vertical asymptote. Why don't I give you just one to find out, to get for us the vertical asymptote? My second activity is here. Just get for me the vertical asymptote. I have, and sometimes you may find yourself having two vertical asymptotes. That one is also very, very possible. So don't say that. Then I have my second activity here, activity 2, y is equal to 4x minus 8 out of x plus 4. You can place for us what your vertical asymptote is. And don't forget it is a line. And when we are drawing asymptotes, members, because we want to show that our curves do not touch that point, we always use a dotted line. You use dotted lines to show that your curve doesn't touch those particular lines. Okay. I think negative for perfect, negative for good. So here, your x, you just say x plus 4 is equal to 0, and your x is equal to negative. So that is our vertical asymptote. Okay, we are going to continue. We have what we call an horizontal asymptote. Now, this is the one that I want us to understand because it has quite a number of conditions. Now, number one, we are going to be observing, one, the degree of either the numerator and the denominator. Those two things are going to be very crucial. Take an example. We are going to be looking at if we have an horizontal asymptote. How do we obtain an horizontal asymptote? Now, there are three conditions that can occur. Let me use A, x power n plus b. Out of C, xc, this is m plus maybe d. when you look at n is I'm using it as the highest power in the polynomial in the numerator. I'm using m as my highest power in the denominator. Take an example, I can give you something like this. I have 2x squared plus maybe 4 out of maybe maybe 3x power 2 plus 4. Now, for such a case, my highest degree in the numerator is 2. Highest degree. You look out for the highest degree. When you look at the denominator, even if I add 4x, the highest degree in the numerator is also 2. So in the numerator, the highest degree is 2. In the denominator, the highest degree is 2. Now, for such a case, when we want to obtain the horizontal asymptote, what do? This is where we divide, and that is the second case. We divide. You look out for this highest power that has appeared, which is x squared. Then you say 2x squared out of x squared plus 4 out of x squared out of 3 x squared out of the x squared plus 4x out of the x squared. That is 1. We are going to look at an example, but I wanted to first bring it to your attention. Number 2, the second case is whereby you look at your highest degree in the degree in the numerator is smaller than the degree in the denominator. Take an example for such a case where I have something like this, whereby when I look at the numerator, for this case now what I've written, you notice that in the numerator, the highest degree is 1. In the denominator, the degree is 2. Now, for such a case whereby the degree in the numerator is smaller than the degree in the what? In the denominator. For such a case, our asymptote is 0. It does not exist. Then the third one. Now, those are the curves. Let me show you how those curves look like. Those are the curves whereby you looked there, but you were not seeing anything along the horizontal, like they were cutting each other. They were cutting each other. An example I can give you is that, let me just put here an x squared. Wait, what is happening? I want to put x squared, something like that. Something like that. I'm just giving you just a rough example, something like that. So when you look at this, since you have 3 curves, you may not know very, very well. But this one's just a rough example. Then you have a case whereby both these, I'm just changing the degree such that you can look at them and see the difference of the curves. When I change, that is how your curve will look like. Now, for such a curve, we shall have our asymptotes very visible. Then we have a case whereby the degree is bigger. Here in the numerator, let me say in the numerator, you have 3 as your degree. We have that case, and that is how your curve looks like. Now, this is where we say that this is where you get your your slanting asymptote. You have this curve, and therefore your line will pass here. But when you find yourself that you have the degree is the same as 2, then it means that you can be able to see your horizontal asymptote for such a curve. You can be able to see it. When you find that the degree here in one of the cases is smaller, then also that one is another case. You cannot see like your Hope members, I think you can look at the graphs, the 2 graphs. When I try to expand them like this, you cannot know which line is there. Because when you look at this curve, you may not say that the line is going to, because it must apply to all curves. So you cannot just say the line is going to pass here. No, not really. Yeah. So those are the different cases we are looking out for. But we can look for how that line, how we can come up with that particular asymptote. So for all those 3 cases I have showed you, we approach them differently, not the same way. Not the same way. So for the first one here, like I've said, we shall not have. As long as the numerator's degree is smaller, then our y will equal to 0. Members, first let me know whether you are picking. Members, are we picking what we are talking about? Members are saying yes, yes. So we are going to look at all the 3 options. Like whenever you have a graph, there are things you need to know. You'll have to get your asymptotes. Whenever we are going to graph, we shall always get these asymptotes. So can we now look at the first example, the first activity? The first activity that I want us to look at, I'm going to use this line again. You have your line y is equal to 3x plus 6 out of x minus 1. And what are we finding? We are finding the horizontal asymptote. Now, if I'm finding the horizontal asymptote, the first thing you look out for, look for the degree. The degree in the numerator and the degree in the numerator and the degree in the denominator. And when we say the numerator and denominator, look out for the highest power. Look at the x's you have. Which one has the highest power? So members in the chat, you tell me what is the highest degree in the numerator and what is the highest degree in the denominator? What is the highest degree in the numerator and what is the highest degree in the denominator? Members are saying 1. All of them are 1s. So that means in the numerator, this is 1 and this is 1. And now, if you find out that the degrees are the same, once these degrees are the same, what do? You get that highest degree and then you divide throughout in all. So I'll come and I say y is equal to 3x divided by x plus 6 out of x divide by x minus 1 out of x. Divide everywhere, yes. Now after here, you are going to notice that I remain with 3 for the first one plus 6 out of x divide by, here I remain with 1 minus 1 out of x. That is for our y. Now, when we are finding the horizontal asymptotes, we are looking at how does x behave as it comes from the infinity. How does x? That means that where there is x, we shall put infinity. So it means we shall have y equals to 3 plus 6. Where there is x, put infinity, divide by 1 minus 1 out of infinity. Now, members, you try code this one on your calculator. 1 divide by, let me say 1000, something very big. When you get 1 divide by a very big thing, members, what is your answer approximately equal to? What is your answer approximately equal to? You notice here you get 0.00000000001. And therefore, members, I want us to conclude that whenever you have 1 divided by infinity, your answer is 0. It approximates to 0. So this one is going to vanish to 0. This one is going to vanish to 0. And therefore, we shall say that our y will equal to 3. So that is it. That is it. Yeah. Then there is a second approach whereby, though sometimes kids make mistake, whereby you identify like another format is you identify in the numerator, you get the numerator divided by the denominator. But in the numerator, you identify this one with the highest power, which is 3x. You divide by down, which one has the highest power, which is x. So you end up with 3. That is the second alternative. Okay, allow me to give you the second activity. Activity number 2. Always identify the kind of what? The kinds of powers you have. Does it need me to have to use this approach, or it needs me to use the other approach? Because it will always depend. It depends. So I have here y equals to x squared out of x squared minus 1. So I'm going to ask members, first identify the degree. What is the highest degree? Always look for the highest degree in the numerator and the highest degree in the denominator. If they are the same, then it means you just divide. Everyone is saying 2 from the chart. So here, this one, numerator highest degree is 2, denominator is highest degree is 2. So what you do, you divide by the highest degrees by the variable of the highest degree. So I will say x squared out of x squared divide by x squared out of x squared. You divide everything you have out of 1 minus x squared. So you end up with 1 out of 1 minus 1 out of x squared. But where there is x, you put infinity. So when you have 1 out of infinity, you end up with 0. So therefore, our y will equal to 1 out of 1, and our y will equal to 1. If you had taken the other second approach, whereby identify the highest degree, carry it with its coefficient is x squared, divide by in the denominator the highest degree, you still end up with a 1. So it depends. What do you want or which approach you want to use? But always better you use the one that you are familiar with the one that you feel is a bit much easier. So that's how we obtain the horizontal asymptote, given our thing is like in that format. But allow me to give you one more again. Oh, wait. May I first create space? May I first create some space? And this one is going to be key in sketching. It's going to be key in sketching. Allow me to create more space such that I can give you the last one, such that members can try it out for me using any of the approaches. I have this. I have. Now, also I want to let you know, members, when you find that your things, your function has not been, let me say, is not factorized, please, you go on, let me say, has been factorized, and you are finding the asymptotes for horizontal. Please first open it up, and then after opening it up, then that's when you can go on and get those asymptotes. Never do it without opening it up. Let me hope that is clear. So let me say I have given you x minus 3 out of x minus 1, x minus 4. Now, once I give you something like that, first expand as you are looking for the horizontal asymptote. So can we find the horizontal? Find the horizontal asymptote. Find the horizontal asymptote. Find the horizontal asymptote. First open, for these ones, identify the powers. That is very important. Identifying the degree. Okay. From the chat. From the chat, what are people getting? People are getting y is equal to 1. Y is equal to 1. Okay, Matthew, your hand is up.
Excuse me, sir.
Yes.
Teacher, like I was not following because I had a network issue. Maybe you can recap for me. Thank
Okay.
you.
Okay. Now, we said we open, so we have x squared minus 3x over, this is going to be x squared, for those who have opened, minus 5x plus the 4. So we said the first thing, identify the degree. So in the numerator, our degree is to the highest degree. In the denominator, the highest degree is also 2. So we said you can use two approaches whereby you identify that thing with the highest degree, you divide it throughout. So here I will divide by x squared minus 3x out of x squared, divide by x squared out of x squared, minus 5x out of x squared, plus 4 out of x squared. So at the end, you'll have 1 minus 3 out of x, divide by 1 minus 5 out of x plus 4 out of x squared. Then you say that for this case, our x is equal to infinity. So 3 divided by infinity is 0. 5 divided by infinity is 0. 4 divided by infinity is 0. So you end up with your y equals to 1. Yeah, that is what I wanted to bring to your attention. And members, always look, there are times whereby it's not always a 1. Yes, Bettina?
So good morning, sir.
Yes, good morning.
My question is, so in case I'm having something like x squared in the in the numerator, but then maybe when you look at my denominator, the coefficient is not 1. Maybe it is 2x squared. Do I still divide by x squared?
Let me give an example similar to that and you do for us. Don't go off, Bettina. I have y is equal to 4x squared out of x squared plus 8. Right? In fact, let me even put here. Okay, can I put here? Okay, this. You tell me, how would you approach it? First, tell me what is the degree in the numerator, what's the degree in the denominator?
The degree in the numerator is 2, and also in the denominator it is 2.
So what are you going to do?
So for me, I would use the other method of saying 4x squared divided by x squared.
That is very okay. 4x squared out of x squared, and you end up with 4. You divide the coefficient, highest coefficient, divide by the denominator. So that is very okay. So even if you are using the division one, you look out for that variable with the highest power that it is x squared. So that's what you divide with. You say x squared, divide by x squared, divide by x squared out of x squared, plus 8 out of x squared. So you end up with 4 out of 1 plus 8 out of x squared. Then this one goes to 0, and therefore you remain with 4.
Oh.
Fine?
Yes, teacher.
And now you need also to be very careful that there are sometimes where you are going to find, let me say, 3x squared plus, let me say, 4x divided by here. Okay, let me put here 3. I'm just giving an example. Plus 2. And then down I have 3x power 3 plus, let me say 2x, something like that. Now, still here, members, even if the number is like that, always first find out what is my highest power. So for this in the numerator, the highest power is 3. So here in the numerator, it is 3. What about in the denominator? In the denominator still, when you look at the polynomial, the highest degree is 3. So since the degrees are the same, still you do the same. You can use the approach, shares this approach whereby you get the numerator divided by the denominator with the highest degree. So with the highest degree, we have 4x cubed. divide by, in the numerator, the one with the highest degree is 3x cubed. So for this case, your asymptote will be 4 out of 3. In case you're using the other approach, it means you're going to divide by x cubed. So that means you say 3x squared out of x cubed plus 4x cubed out of x cubed plus 2 out of x cubed out of 3x cubed out of x cubed plus 2x out of x cubed. So here, you'll get x squared, you remain with 1x. So here you'll get 3 out of x plus 4 plus 2 out of x cubed divided by 3, then plus 2 out of x squared. So when you put in infinity, this one goes, this one goes, this one goes. So you remain up with the 4, down you remain with the 3. So you take note of that. Okay. Yes, Shadow?
Good morning, sir.
Morning.
I was asking about if you have like x squared, do you need to, when you're replacing with an infinity, you can put infinity squared, or you just, yes.
It is okay, or you can ignore it to put the squared.
Okay, thank you.
All right. Okay, so let's look at the second case. That was one whereby the degrees are the same. What about when the degree is different? An example, y is equal to 1. Oh, because I'm making notes. Let me use the permanent pen. Y, sorry. Y is equal to y is equal to 1 out of x plus 2. So members in the chat, you told me, what is the degree in the numerator? What is the degree and what is the degree in the denominator? What is the degree in the numerator and what is the degree in the denominator? Joan, that is very true. When I only consider the number of degrees, that yes, that is very true. Leave out. Members are saying 0 and 1. Very good. So here you're noticing that up is 0, down is 1, because here there is an hidden x to power 0. Now, we say that when the degree in the numerator is smaller than the degree, still you do the same thing. But here I'm just bringing it to your understanding. Is that, what does it mean? It means that as x tends to infinity, where there is x you put infinity, it means you have y is equal to 1 out of infinity. Infinity plus 2 is infinity. So 1 divided by infinity, we said is equal to 0. So that's why y is always equal to 0 whenever the degree in the numerator is smaller than the degree in the denominator. Hope that is okay. Hope that is very okay. So for you, the moment you observe and you notice that the degree in the numerator is smaller than the degree in the denominator, your horizontal asymptote will always be a 0. Very good. Okay, why don't I give you this one and you try, can you tell me, what about members I have x plus 2 out of x into x plus 3? What is our horizontal asymptote? What is the horizontal asymptote? What is the horizontal? Very good. It is 0. Thank you. Thank you. Thank you. But you may not, don't even cram. Even if here, this is x plus 2 divided by x squared plus 3x. Now, for such a case, still, even if I want to prove it, I use the highest power. I say x out of x squared plus 2 out of x squared divided by x squared out of x squared plus 3x out of x squared. In case I'm proving it, I want to show. So this is 1 out of our x plus 2 out of x squared divided by 1 plus 3 out of x. So when you put infinity, you get 0 up. So up we shall have 0 divided by 1 because 3 out of infinity is 0. So which is equal to 0. Members, are we good to continue? Is that fine to everyone? Is everyone happy with that? Same page. Very good. Now let us look at the last case. Now, the last case is the case whereby the degree in the denominator, when you look at your denominator, the degree is smaller. The degree is smaller than what you have in the numerator. That is the case. So that's the case we are going to look at for. Take an example. I have y equals to x squared plus 2x plus 3 divided by x plus 1. When you look at that, what is the numerator degree and what is the denominator degree? You look out for the highest degree, always read off the highest degrees. 2, 1. Very good. In the numerator, the highest degree is a 2. In the denominator, it is 1. Very good. Now, whenever the numerator's degree is greater than the denominator's degree, what do? Here, we use the division, the long division to get the asymptote. And for such a case, those are what we call the oblique asymptotes. So here, you are going to use your long division. Hope you remember. So here, we shall have here x plus 1, and then here we shall have x squared plus 2x plus 3. Now we start. Now, you remember when we are dividing such polynomials, I'll have this inside, I first divide it with x. So I will say x squared divided by x. I end up with x. So that means that up here, I'm going to write my x. After getting your x, you get this x, multiply it again. So you get your x now, I multiply it with x plus 1. So here I get x squared plus x. So at this point here, we are going to have x squared plus x. And what is your target? Your target is, don't cram that always you have to subtract members. Always, what is your aim? Is to eliminate x squared. So since this is plus, positive, same signs, I subtract. Once I subtract, I'll have 0. 2x minus x, I will end up with an x. 3 minus 0, I end up with a 3. So we shall end up with x plus 3. I go back again, I will get this one here, I divide with this. So I say x divided by x, I end up with 1, and which is a positive 1. So here, I'm going to end up with a 1. Now, this new one I have obtained, I multiply it with this. So I say 1 into x plus 1. So I end up with x plus 1. So that means that at this point here, I'm going to have here x plus 1. And since the coefficients are the same, I will subtract x minus x is 0. 3 minus 1 is a 2. Now, the moment I reach at that point, it means that I will stop at that point. And therefore, I'll go on and I read off my... don't mind about the remainder. Just read off what you have obtained here. And now this one is what we call our asymptote. And therefore, our asymptote for this case will be y is equal to x plus 1. And this is what we call a slanting asymptote. Members, let me know. Are we there? You looked at long division, I think in term 1, somewhere there, when you are looking at polynomials. Okay. People are there. Okay, yeah. Okay. Okay. You can first write. As I give, we shall do this one together, but I want people to be trying out. You look at the degree. Our second activity is here, activity 2. I have y is equal to 3x squared plus x plus 2 divided by x minus 1. So I'm interested in you getting for me the slanting asymptote. Look at the power in the numerator. It is 2. Denominator is 1. Then that means that the asymptote is going to be a slanting one. So can we find it? Okay. from the chart, people are getting 3x plus 2. Very good. 3x plus 2, 3x. It is a plus 2. It is a plus 2. Allow me to put 1. I'm going to be doing this one, but for those who have got 3x plus 2, kindly, I want you to go on this one here. And for you, continue with this one as I explain to people who are failing to get the other one. Yes. So like here, for you people who are finished, do the one in green. And so those who are not getting there, we said you put here your x minus 1, and then we shall have our 3x squared minus x plus 2. Then get this one here, which is 3x squared, divide by this x here. So when you divide, you end up with 3x. So here up, we shall put our 3x. Now the 3x we have obtained, get it and say 3x into x minus 1. So you end up with 3x squared minus 3x. It is the one that you are going to bring here. So I'll say 3x squared minus 3x. Since you want to eliminate the x squared, it means you'll subtract. The coefficients are the same. So when you subtract, you'll have here negative minus minus. I think that is where people, it is negative x minus minus 3x. So this gives you a negative x plus 3x, which gives us a 2x. So here I'll remain with my 2x plus 2. Then I'll have this 2x here divided by x. So I set 2x out of x, which gives us a 2. So that means that up here, I'm going to come and say plus 2. So when I finish that, I'll get that 2 I have obtained. I multiply it by x minus 1. So I have 2x minus 2. So what will I end up with? I'll end up with 2x minus 2. Then when I subtract, because I want to eliminate the x, I'll get 0. Here I'll end up with a 4. 2x minus 2x, 2 minus minus 2 gives me a 4. And therefore, I don't mind about this remainder. I look out for what I have here. And I say my y is equal to 3x plus 2. Okay. Hope that is okay. Santos, that's okay. Matia. Okay, 3x minus. Oh, you people, you are very good now with division. Yeah. Okay, perfect. 3x minus 1. That is very, very true. If you are getting 3x minus 1, that is very, very fine. That is very, very fine, and that is true and very correct. Okay, okay, okay. Now this one, you'll do it. I'm just giving you one just for your, oh, okay. This one is just for your homework. But I think, did you write about a brick? Maybe just take a screenshot. Because these are the ones we have been dealing with. Just take a screenshot. You'll pick something, but make your own notes. You have seen how we get them. You have seen how we get them. Just make your own notes. Make your notes about a brick, but allow me to give you this one as your homework that you'll try out in your free time. I have y is equal to x cubed minus 3x squared plus 2 out of x squared minus 1. So that one will be just your homework to try out. And your answer will be x minus 3. Okay, but before we continue, I want to know whether we are on the same page. There is anyone we are leaving, kindly ask. Because we are building up the foundation for curve sketching. Anyone we are leaving behind? Okay, are we good to continue? Okay, let me first pick on Lydian. Yes, Lydian? Unmute Lydian. Okay, okay. Okay, I'll fail to get Lydian, but people are saying, oh, someone wants me to take back the screen. Okay, just take a screenshot.
Excuse me, teacher.
Yes, please.
Morning.
Morning.
Why don't we consider the remainder?
Oh, like the remainder doesn't have like any impact on the line or on the equation. It doesn't have any impact on the equation because our interest is how does that equation look like? That's the only thing we want. And for us to get that equation of a line, you just need the intercept. So that's why we ignore the remainder completely.
Okay, thank you.
Okay. So take a screenshot. These are going to be your numbers for trying out as well. Now, what I want you is whenever we obtain a function, we should be in position to find either one, okay. I don't know whether you need to do together. But whenever you find a function, one, find the vertical asymptote. That is the first thing. From there, then establish, am I getting a horizontal or am I getting a, can we? Okay, but I know, you know what to do. Yes, R.
Teacher, do they always tell you that asymptotes they want you to find, like
They
vertical or
don't.
horizontal? Like, do they make it clear or you're supposed to figure?
You have to find them yourself. They don't. Is that fine? They don't. But one,
I'm saying,
yeah.
how do you know which one they want you to find?
No,
How do
now
you
you
know the
read
one they
you
want you
read the
to find?
function. It is you to read the function. But one thing you always need to know is that you'll always have a vertical asymptote. That is one, automatic. Because always you'll have to equate your denominator to 0. Secondly, is that you look at the function you have. Then you ask, what are the degrees of the highest powers? If they are the same, then it means that one, a horizontal asymptote exists. So you find it. So you find your vertical asymptote and then the horizontal asymptotes. You have to find it too. Then, if you look at the second one, look at you know that here you'll get your vertical asymptote. What about which other asymptote? Is it going to be horizontal or it's going to be oblique? So now for you to read the behavior of the curve, so either it is vertical and horizontal, or it can be vertical and oblique, depending on the nature of the functions you are dealing with. Alright, is that fine? Okay. Let me hope, Ara, that is okay. Always look at whether it is this function or it is that is the one that determines. But here they will not tell you that find the horizontal. No, it is from you to find those particular ones.
Yes, teacher, it's fine.
It is
Thank you.
fine. Okay, yes. And you need to be very observant now. Which one am I using? That I'm using this. Which one am I using? I'm using this. And you know that the approach always differ depending on the number. Kale, I think you have taken a screenshot. Please, you'll continue. Oh, people ask, members, do you need to try out one number here? Let me know through the chat, or we can do it as our exercise. Let me know through the chat whether you want us to try out any number or exercise. People are saying exercise. No, exercise. Okay. Kale, do it as an exercise. Yeah, okay. Now, the last bit of it we are going to look at briefly is what we call the turning points. I do know and I understand that members, you have looked at turning points. You know how to differentiate. So that is one thing I am sure about. But as we look at turning points, just to remind you that for us to get our turning points, I'm just reminding you that for turning points, always our dy dx is equal to 0. Now, the second thing you need to know that about turning points, you need to know the nature of the turning point. The nature of the turning point. Points or what? And here it is up to you. Either, but the best one, depending, you can either use the table or you can go on and get the second derivative. So any approach of your choice here will work for you. Now, those are the things that you need to know. Allow me to use one number and then we know the nature of those particular points. I can use just one example and then that one will help us to, it will remind us a bit. And then from there, we'll go on. But the most important thing, you need to know how to differentiate because no one is going we shall not look at differentiation again. But I do expect that as an individual, you have mastered very well how to differentiate. How to differentiate. Yeah. Yes. Yes. So that is going to be my assumption. Okay. Okay. And sometimes also you'll find out that not all points will have turning points. Sometimes you may do things and you don't find any turning point for that particular thing you have. It is very cool. Okay. We look at activity 1. I have y is equal to x squared out of x squared minus 1. And what am I looking for? I'm looking for the turning point. So what are we going to do? We are going to differentiate. So members, let me know which approach do you want to use to differentiate this. But everyone, you can use yours. You can use yours. Should we use quotient? We use natural log. It depends on what you want. People want natural log. Okay, so we are going to use natural log. So I'm going to introduce natural log on both sides. I said natural log of this is equal to natural log of x squared out of x squared minus 1. So we shall have the natural log of y equaling to natural log of x squared minus the natural log of x squared minus 1. And therefore, we differentiate. So we shall have 1 out of y dy equaling to 2x out of x squared minus 2x out of x squared minus 1, but everything with respect to the x. So my dy dx will equal to, here I will divide by x, I'll have 2 out of x minus 2x out of x squared minus 1, then times y. So when I continue, I'll have my dy dx is equal to, I can first simplify what I have in the brackets, and members will agree that is 2x squared minus 1 minus 2x times x out of x into x squared minus 1. Then everything I multiply times y. So when I open, I'll have 2x squared minus 2 minus 2x squared out of x into x squared minus 1. Then if I multiply times my y is x squared out of x squared minus 1. So you notice that this and this are going to cancel. I remain with negative 2x squared, and down I'll have x into x squared minus 1. But since they are 2, I'll put a squared here. And therefore, this x and the 1 up will reduce. So I remain with negative 2x out of x squared minus 1, everything squared. I first paused at that point, as you also finalize your differentiation. And finalize your differentiation and check out whether we are getting the same answer. finalize your differentiation and check out whether the answer is the same. It is the same. Okay, good to go. Now, after us obtaining our dy dx, so we have said our dy dx was equal to negative of 2x out of, x squared minus 1, x squared minus 1, everything squared. So you know that for our dy dx, we shall always go on and equate to 0. So we are going to equate this function to 0. And what will happen? We find out whether we have turning points or we do not have turning points. So we shall say now at dy dx is equal to 0, we shall have negative 2x out of x squared minus 1 squared is equal to 0, and therefore we have negative 2x is equal to 0, and our x is equal to 0. So that means that our x is equal to 0. Then we go back. Remember, we want a coordinate, a turning point. We had x squared out of x squared minus 1. So when you substitute in x is equal to 0, our y will be 0 squared out of 0 squared minus 1, and therefore we end up with a 0. So that means that your turning point for this particular curve is 0, 0. Now, the next is to find out what is the nature of this turning point. So, nature of the turning point. So, how do we get the nature? I'll come like this, like this, like that. I draw my table. After drawing my table, allow me, for me, I'm going to use the table. I don't want to do the differentiation again, but if you want, you can do that. Now, what do we have? I'm going to come here. I have here my dy dx, and I have here my point, and my x is equal to 0. So what do? You choose a value, like this is where 0 is, like the way you know the axis. Choose a value less than 0 and a value greater than 0. Let me say here I've taken my x to be negative 1 as my value. I'm just using that. Get this one, put in your dy dx. So I'll say my dy dx is equal to negative 2x out of x squared minus 1. So when I put in negative 1, I'll have negative 2 times negative 1 out of negative 1 squared minus 1, everything squared. So what do you notice? When I put in negative 1, you notice that negative 1 cannot work. Our function goes to infinity. Then it means that this is not an appropriate value to use. So that means that you cannot use negative 1, because that negative 1 makes this function to vanish. So you can maybe say, what about when I use negative 2? When I use negative 2, up there, I'll have negative 2 times 2, and I'll have negative 2 squared. So I end up with 4 divided by, this is 2 squared, which is 4 minus 1, which is 3 squared, which is 9. Now, this value we have obtained is a positive value. So here I will say this is positive. When you put in 0 here, you notice that your function for your dy dx also will give you a 0. So it gives you a flat. So here it is 0. I may not put anything, but when you put it there, you get a 0. What about a value above? Now, for such a case, you can't use 1 because 1 will make the function vanish. So use a value either above 1. Let me say I've used x is equal to 2. When you use x is equal to 2 and you feed it here, where there is x, you put 2, you get your answer as a negative. Now, from there, you need to know, how does the gradient move? That when I have a positive gradient, my line will always look like that. That is for a positive what? A positive gradient. When I have a So this is like that. When I have 0, I have a line like that. When I have a negative, my gradient will look like that. That means that the nature of your curve will look like that. So it's going to be a maximum. So that means that the nature of that turning point is going to be a maximum. Yeah, I don't know whether we're on the same page or we are leaving someone behind. Any questions on this? Same page, same page. Same, very good, yeah. So, that is good, that's good, we are good to go, same page, So now, when it comes to the turning points, I'm going to ask you that you first practice. You have looked at turning points before, so I'll ask you that you practice these turning points such that you know exactly what to do with them. With them. So that is just briefly about these turning points. Yeah. Why don't you allow me to just give you this? This is just your exercise as well. Oh, wait. I don't want to give you this. I don't. Oh, where should I write? Eh, Okay. Oh, we beautify one question here. I don't know whether we can beautify. And that for each of these ones, also find a turning point, and the nature. We can make it like that. For these questions, you're going to do find the turning point and also go on to find the what? The nature of those turning points. Yeah. Yeah, that one will be enough. That one will be enough. And there are cases where you will not have a turning point. So those cases also exist. Take an example. Once you differentiate your thing, and then like you end up with your dy dx as 3 out of x minus 1. I'm just using this as an example. Now, for such a case, you notice that when you say 3 out of x minus 1 is equal to 0, you see 3 is equal to 0. Now, for such a case, your conclusion is not turning point. Hope you have got it. The moment you equate this and you notice that there's nothing you are getting for the value of x, then it means that we don't have a turning point. So for such a case, you say, I have no turning point. Let me continue. You just conclude, not turning point, not turning point. Yeah. So members, we are going to end there. We are going to end there for today. So for these numbers, find the asymptote, find the why don't you, in fact, and once we have those ones, just know we shall have come up with a graph. So tomorrow we shall do some 2 graphs. We shall do 2, you do 1, such that by Friday we must know how to, we must be very good with drawing the graphs on our own. Yes. So Samsung ask. Samsung ask.
Oh, sir, it's not a good morning, sir.
Yeah.
Teacher, it's not a question. I just want to know the previous answer. What was the answer of the previous question? Where
Oh,
you
which,
used the link?
where we use the lean?
Yes.
Hey, what do you have? What do you have?
Because I've stopped on where I got -2 over. It was x cubed minus x.
Did you get this? When you
No,
differentiated?
I have a 2 up only without an x.
Which approach did you use?
I used
Quotient
the
rule?
yes.
Quotient rule. What was your u and what was your v? Okay, what was your du?
Mine
Okay.
was
Your du dx, what was it?
2x.
What was your dv dx?
2x.
So we go back. So you had your v du dx minus u dv dx out of the v squared. We substitute your v,
X squared minus 1
your du dx,
into the x.
2x,
2x.
minus your u,
X squared
times
2x over
okay, x squared minus 1 squared.
squared, yes.
Open for me the brackets here up for this first one here. What do you have?
2x cubed
2x cubed, minus
minus 2x
2x, minus.
minus 2x cubed.
Okay. Are you seeing this and this?
Yes.
They end up giving you?
Oh, oh, sir, I have seen the mistake.
What was the
I had
mistake?
the 2x up, but I neglected it downwards. But I think it was an error, not intention.
Oh, okay. Sorry. Okay,
Thank you,
okay.
sir.
Kai.
Ah.
Okay. Yeah, members, have a blessed day. Let's end here. See you tomorrow and let's practice how to get those asymptotes. Bye bye.